Hello, and a warm welcome back to my YouTube channel. Just you're all well and in good spirits. Today we're going to be having a look at electromagnetism and some of the electromagnetic effects which we have been studying at IGCSE Coordinated Science Physics, code number 0654. Okay, first question, draw the magnetic field of the solenoid in figure 1. So solenoid, we have the wire wrapped around a hollow cardboard tube. We can see the currents going in on the right hand side and coming out on the left. So I'm going to be using one of my hand rules. Here's my left hand, here is my right hand. Put my left hand away, here's my right hand. The current is going around this way. It's going around this way around my hand. And my thumb is pointing in the direction of the field. So I can draw the field coming out there and going in here. We can draw some more lines on there to show the direction of the magnetic field. Okay, B, figure 2, two iron rods placed inside a solenoid. Explain why the iron rods move apart when the switch is closed. Okay, if we have iron rods and we have a current going around the outside in close proximity to them, then we have induced magnets. Induced magnets. The magnetic field is induced on the iron rods. Do not put that they are charged. Some kids put that, don't do it. They have induced magnets or induced magnetism or induced magnetic field by virtue of the current going around the outside. You could go on to say about the poles. They would have the same, because they're in the same direction of the flow of the current, they have the same polarity at each end, which means they would start to move apart. So explain, that's my command term, explain why the iron rods move apart. The current flows, induces a magnetic field, they're not charged, it induces a magnetic field, and they will have the same polarity at either end. I suppose they would repel. A student investigated the strength of an electromagnet. The student investigated how the strength depended on the current in the wire, the number of turns of the wire around the core. This is a standard question. They like to give you a circuit with power supply. Power supply is here. Ammeter in the circuit, so you can monitor the current, which is I. We have weights, and we also have a soft iron core, which is able to be magnetized. The following table shows the results. So 1 amp, 30 turns, 6.5 newtons, 1.5 amps, 20 turns, 6.4 newtons, and 2 amps, 10 turns, 3.7 newtons. So the student has changed the current, and they've also changed the number of turns. Explain why the method used by the student is not valid. It's not valid because the student has used what we call independent variables. Don't forget, independent variables are the things that we choose to change as part of our experiment. The command term here is explain. Previously it was describe, now it's explain. Have we explained? No, we haven't. We've just stated. We've stated there are two independent variables. That's the problem. That problem means we cannot tell which of the independent variables, let's call it the IV, have produced the effect. Was it changing the turns on the wire? That's had a consequence to the maximum weight in newtons, or was it a change in current in amps, which had an effect on the maximum weight in newtons? It's impossible to tell because the student did not keep just one independent variable changing. They chose two. Okay, moving on. How does increasing the number of turns of wire from 10 to 20, no, that's not the one that we're doing. That's better. How does increasing the current in the wire affect the strength of the electromagnet when the current has 30 turns of wire? Let's have a look at the graph. We've got 30 turns of wire here more turns, more weight in newtons, more currents. That looks good. 20 turns seems to follow a similar trend up here, but clearly 30 turns carries more weight. And 10 turns has a similar increase in terms of weight in relation to current, but is nowhere near as profound an increase or an amount in weight in newtons. What does the question say? How does increasing the current in the wire, so this one, affect the strength, so I guess that's how much it can weigh, of the magnet when the electromagnet has 30 turns of wire? Well, I would say if you increase the current, so increase I, which is current, then we increase the strength. I would also say that we increase the strength, this is for 30, because look at this portion of the graph here, we increase it up to a maximum. It would appear that even with increasing current from around 2.75 up to 3, we are still lifting around 11 newtons, which is here. There's no increase for an increase in current with 30 turns. Probably a bit more than needed for 1 mark, but it's okay. E, how does increasing the number of turns of wire from 10 to 20, remember that big gap? So we've got 10 here, 20 there, there's a big increase, 10 to 20. Affect the strength of the electromagnet compared to increasing the number of turns from 20 to 30. Well, we can see there's a much bigger gap, 10 to 20, and a much smaller gap between 20 and 30. So what are you going to write? So we need to get the pen ready, Mr. Midgley. There we go. So if we go from 10 to 20, this is much, much greater than the change from 20 to 30. You could go into it doubles, it triples, I can't remember what the relationship was, but as long as you're saying it's much greater than, so there's terrible greater than symbols, let's write that in for you as well. The change from 10 to 20 is much, much greater than the change from 20 to 30. Have we compared? Yes, we have. Did we get the mark? Yes, we did. Question 2. The diagram shows apparatus set up by a student. We can see that there are 2 magnets set up here with a free standing wire in between, which is held between the magnets. Could be held with clothes pegs, paper clips, doesn't matter. And closing the switch creates a force that acts on the wire XY. I'm thinking, which hand? Which hand? Which hand? Explain why a force acts on the wire XY when the switch is closed. So, if I close the switch, what happens? A current flows. Electrons are moving around the circuit. Close the switch, a current flows. If a current flows, what does that create? It creates a magnetic field. If there's a magnetic field in this wire between X and Y, it will then interact. That magnetic field, temporary magnetic field in the current carrying wire, will interact with the external permanent magnetic field. 1, 2, 3 marks. Close the switch, current flows. Current flows creates a magnetic field. That magnetic field induced in the wire interacts with the external permanent magnets, creating movement. Part 2. The force causes the wire XY to move. Draw an arrow on the diagram above to show the direction in which the wire XY is going to move. Not right-hand rule, because right-hand rule is purely current field. Current thumb is the field. Back to my left-hand rule here. My thumb is movement, forefinger, magnetic field, second finger is for the direction of the current. Okay. Draw an arrow on the diagram to show the direction in which the wire XY will move. So we have, I'm trying to put it onto the diagram here, can you get the field lined up north to south? You can. The current is going around here from positive to negative, remember it's conventional current, and therefore the movement is going to be directly upwards. All that for 1 mark. State the effect that this experiment demonstrates. Every student will put, this is the motor effect. I think anybody that puts the catapult effect should get an extra mark. You don't, but I think they should. Okay. B. The student replaced the battery with a low frequency alternating current power rather than DC direct current, and the student closed the switch. Describe the movement of the wire. It's going to do that, isn't it? Because rather than the current being in one direction, it's going to be alternating, hence the name alternating current. So it's going to be vibrating. You could say moves up and down also. That's good. Give a reason, because as the current's changing, the direction of, you got it, the magnetic field is also changing. Okay, part 3. Figure 1 shows a straight wire passing through a piece of card. This is in every textbook. A current is passing through the wire. It is. Current I is going around in this direction. Describe how you could show that a magnetic field has been produced around the wire. 2 methods I hope you are familiar with. One is plotting compass. One is iron filings. What's the command term? The command term is describe. Have we described? No, we have not. If you just put those 2 things, 0 marks. Nothing. Because the plotting compass, the pointer will line up with the magnetic field. So it's not enough to say plotting compass, you have to say what happens. And the iron filings, if you tap the card, they will line up also with the magnetic field. Okay, describe, keyword. Figure 2 shows the ignition circuit used to switch the starter motor on in a car. Go Elon Musk. The circuit includes an electromagnetic switch. Explain how this works, and you're going to get this. Total for the question is 6 marks. This aspect of the question is 4 marks. Lots of students throw lots of marks away on these things here. And when you tell them the answer, they go, oh, I knew that. So, write it down. What's the first thing that we should write? You get a mark for saying, close the switch. Bing. Close the switch. Close the switch. What happens? The current flows. If the current's flowing around here, that means that the iron core is magnetized. So soft iron will not make a permanent magnet, but you can easily magnetize it using a current carrying wire. So iron core is magnetized. Then what's going to happen? This becomes a magnet. It's going to attract the arm there, isn't it? So iron core will attract the iron arm. Because this is not soft iron, this is hard, it could be steel. And it's going to be attracted here. If it attracts it here, this comes down, that's going to go out, isn't it? If that goes out, then it's going to make that the starter motor contacts, well, they're going to connect, aren't they? The contacts are going to pinch together. If they pinch together, if these come together here, that means the circuit is now complete. Aha! That means, again, we've seen this twice already, the current flows, and therefore the starter motor turns, and your car will begin its journey. Okay. Question 4. The left-hand rule, great, it told me which one to use. Left-hand rule, keep them 90 degrees to each other, kids. Can be used to identify the direction of the force acting on a current-carrying conductor in a magnetic field. Use the words in the box. Oh, it's a gift. They even gave me the words in the box that I am to use. First finger is the direction. Oh, they give me it like that. They give me it like that, cheeky monkeys. The first one is the field. That's the magnetic field. The second, this is your forefinger. Forefinger field. Your second is current. Okay, current. And your thumb is movement. That's how I remember it anyway. Hope it works for you. Figure 2 shows an electric motor. Draw an arrow on figure 2 to show the direction of the force acting on the wire A, B. Ah, okay. So what have we got to do here? We've got our north to south. That's my field. So I need to put my field, forefinger field like this. I can't implant my hand on the diagram, unfortunately. The field is here. The current's going in that direction. So the direction of movement is going to be down. Left hand, not right hand. Left hand. Draw an arrow. Done that. Suggest 2 changes that would increase the force acting on wire B, AB. Well, you could increase the volts or the potential difference. You could increase the current or I. That would work. Or you could increase the strength of, yes, magnetic field. Strength of the magnetic field. Suggest 2 changes that will reverse the direction. So we're going that way, we want it to go that way. We could reverse the poles of our magnet, or we could reverse the poles of our battery. Both of which would change the direction of movement of wire AB. C. The student used an electric motor to lift a mass. That's happened once before in this paper already. This is shown in figure 3. The student varied the electrical input power to the motor. For each different electrical input power, he recorded the time taken to lift the mass and calculated the output power of the motor. So we can see here we've got 20, 40, 60, 80 watts. Work done in joules is 24. Time taken decreases from 2.4 to 0.2. And the output power goes from 10 to 120 watts. Okay. Calculate the efficiency of the motor in test D. So efficiency is output over input. Output over input. Times 100, which is 120 over 80 times 100, which is 150%. When I first did this, I thought, that can't be right. How can you have 150% efficiency? You can't have more than 100% efficiency. That just doesn't work, does it? But we've used the sum, we've used the formula is correct, so let's see where we're going with this. Comment on your answer. Aha, right. How is output greater than input? I think the student did something wrong, look, because we've got inputs 20, output 10, input 40, output 20, input 60, output 30, input 80, output 120. What did the student do wrong? Suggest the reason for this anomalous, it is indeed an anomalous result. Well, what could the student have done to produce the result? To give us 150% efficiency, which is clearly incorrect. I think the stopwatch was started late. They were distracted by something else happening in the laboratory, or maybe they got bored and they stopped it too soon. That's also a good answer. 5a. Electromagnets are often used at recycling centres to separate some types of metals from other materials. They are. Give one reason why an electromagnet would be used rather than a permanent magnet. Well, a permanent magnet would be great for picking things up, but you'd never get them off again. So you need to be able to control whether the magnet is on or off, so you can pick the things up and you can drop them. Job done. In this question, you will gain marks for using good English, organising information clearly, and using scientific words correctly. Maybe you've done this experiment at school. I know my kids did just the other day. Describe how the students could build an electromagnet, including your answer, how students should vary and test the strength. So, keywords. Keep looking at the command terms here, kids. Describe, can do that, okay. Include in your answer how would vary and strength. Okay, so that's going to be 2 marks for how you make the electromagnet, 2 marks for how you vary the strength. It's great strategy to plan out your answer. It's going to be 6 marks. That's a big lump. And then finally, you want another test of the strength, or how test the strength. And that's where my 6 marks come from, 2, 4, 6. Okay. So how are you going to make it? You're going to take your nail, this one, go green now. I'm going to take my nail, I'm going to take some insulated wire, I'm going to use the connecting leads, I'm going to use the power supply, and you could use a circuit here, that would be nice, and you've got the nail, let's try and use a different colour here. You've got the nail, which is in there. You connect that to the circuit, and then around the nail we put coils of the insulated wire, turn the switch on, and not only have we made an electromagnet, we've got our 2 marks for how I make it. How do I vary the strength of the electromagnet? Well, to vary strength, there are a few things we could do. We could change the current I, we could change the volts V, or we could change the number of turns. That would be great. How can I test the strength of the electromagnet? Well, you can change the number of paper clips, increase the current, see how many it picks up, decrease the voltage, see how many it picks up. You can increase the distance. What do I mean by the distance? The distance from the nail to the paper clip. So here's your electromagnet, paper clip here, paper clip here, paper clip here. Vary the distance, D1, D2, D3. Have we got enough for 6 marks? 2, 4, 6? Yes, we have. Figure 1 shows 2 paper clips hanging from a bar magnet. It does. Label the north and south poles of both paper clips. Well, hopefully this is straightforward. If this was south, they would be there. They'd be repelling it. It would just shoot the darn thing off, right? So it can't be. So that must be north. And if that's north, that must be south. If that's south, that must be north, and that must be south, and so on. I got my 1 mark. A. Label the north and south poles of both paper clips. Done it. Student investigates how the number of turns of the wire on an electromagnet affects the strength of the electromagnet. They did. Figure 2 shows the equipment used by the student. So they've fixed the electromagnet in space using a retort stand and clamp, which is here. They've kept the number of turns, probably constant, on there, near the paper clips hanging from it. They've got a variable resistor here, which will change the current, because they're doing the amps. Kept the current through the wire constant, so monitoring the current I here. Okay, what's the question? So as the strength I counts the number of paper clips, explain why it's important that the paper clips were all the same size. Why do I want to be the same size? Well, we want to have the same mass, because that's a control variable, CV, control variable. If you don't control your variables, it will not be a fair test. The table below shows the students' results. 10 to 40, number of clips 3 to 12, so 4 times 4 times. Ooh, that's quite a nice relationship, isn't it? Describe the pattern. Well, increase the turns is increase number of paperclips. Happy days, that give me a mark. I would also go on to say it's a linear relationship, and I'd say times 4 turns equals times 4 on the clips. So that would be an excellent answer for that question. Part D, the student then used 50 turns. So they increased the number of turns, 50 turns on the electromagnet. It picked up 18 clips. This was more paper clips than the student had expected, okay, which was most likely to be a reason for the increase in the number of clips. The paper clips used with 50 turns were larger than the others. Well, no, because that would be less. There were less than 50 turns of wire. No, that would be less. Some were already magnetized. That looks good. And that's a problem with this because students do it over a number of lessons. The paper clips used, the technician puts to that particular practical, and all of them become magnetized because they've been in a magnetic field, and that's one way to make a magnet, as you all know. Okay. Part E, the students repeated the measurement of 50 turns of wire 3 more times. This gave her the following set of results. Explain why the student should now do with the 4 results of the turns of wire. Well, I particularly don't like that one. Why do we not like 18? Because it's 4 away from 14, 2 away from 16, 3. It's an anomaly, isn't it? That's an anomaly. So remove the anomaly. Then I would take the mean of 14, 15, and 16, which is clearly 15 turns. Okay, we shall leave it there. I hope you found that useful. Don't forget, smash that subscribe button at the bottom. Keep working. It's only electromagnetism. Without it, you probably wouldn't have got to school today. Okay, thanks very much for listening. Have a great day.